Ok. Ya. Buenos días a todo el público latinoamericano, todo nuestro público que nos sigue. Esto es la red LAFMAT, Red Latinoamericana de Física, Materia Condensada y Ciencias Materiales, red LAFMAT, conformado por distintas universidades latinoamericanas. En Perú, la Universidad Nacional Mayor de San Marcos. En Chile, la Universidad de San Sebastián. En Chile también la Universidad Católica del Norte, en Antofagasta. En Brasil, la Universidad Federal Fluminense, con el amigo Mario Reis. En Brasil también la Universidad Federal Rural de Río de Janeiro. Y la Universidad Federal de Pernambuco. Venezuela, la Universidad de Zulia, Venezuela. En Colombia, la Universidad Nacional de Colombia. En México, el Cinvestav de México y el Centro de Materiales en México. Bueno, espero no olvidar varias universidades más que están ahí. Si me olvidé algunas, disculpen, los voy a mencionar al final. Bien, el día de hoy tenemos la palestra de una invitada. Ella es la doctora Vivian Andrade. La autora Vivian Andrade estudió su maestría en ciencias en la Universidad Federal Fluminense en Brasil. Estudió su PhD en física en el Instituto de Física de la Universidad de Porto, en Portugal. En 2019 terminó. Sus investigaciones versan sobre materiales magnéticos nanoestructurados. Tiene amplia experiencia en métodos de caracterización y propiedades magnéticas de los nanomateriales. Actualmente ella es postdoc en física en el Centro Brasileiro de Pesquisas Físicas en Brasil. Ella trabaja en el grupo del profesor Flavio García, en el CBPF. Bien, bienvenida Vivian Andrade. Welcome, Vivian Andrade, and you puedes empezar tu charla ahora.
Thank you, Luis, for the introduction. Thank you for the invitation. I hope you enjoy my talk today about the thermal switches for magnetic refrigeration and experimental evidence. So for my talk, I will start with a brief introduction on the motivations for study solid-state technologies for refrigeration, mainly the magnetocaloric effect and thermal switches components, and then how to couple both of the systems, and then the conclusions and future perspectives in the end. So it's well known that currently the conventional refrigeration systems are based on the compression and expansion of harmful gases, HFCs, EFCs, that contribute to the global warming. So in this sense, in 2018, the UN Environment section made a brief note, that around 17% of the energy consumption worldwide is for refrigeration. Today, this will be around 25%. So, and over 40% of the refrigeration system is responsible for the CO2 emission. And with the overpopulation and the global warming, the projections are for this to increase to 37%, which will correspond to an increase from 7 exajoules per year, 12 exajoules per year, only for refrigeration consumption. So it's drastic. We found alternatives that are environmentally friendly and energy efficient. And in this sense, the solid-state technologies are well accepted around the community, the scientific community, that they are the most I forgot the words in English, promising materials to substitute the gas compression systems because they're silent, they are more efficient, and they're also reusable because we can reuse the solid materials for other things. So we have mainly 3 types of solid state technologies. I will talk briefly about some of them. So the thermoacoustic one uses the sound that goes from one side to the other, and then we have some solid plates that are responsible for stocking the heat in one side and then releasing the heat in the other. But these devices are really big, are really huge. We have some groups trying to reduce their sizes, but then they become more complex. So they are not the ones to be used in a refrigerator to substitute our conventional devices. Then we have the thermoelectric. We well known as the Peltiers that we use, and they are commonly used for small devices. So they don't have the potential to substitute the refrigerators in the conventional size that we have today. In this sense, the caloric materials are the most prominent to substitute these gases. And then we have the magnetocaloric, mechanocaloric that still divides in barocaloric, elastocaloric, and torsocaloric, and the electrocaloric. In the sense of prototypes, since 97, the number of prototypes in all of these caloric materials have been increasing, mainly because of the discovery of the giant magnetocaloric effect on the gadolinium 5 silicon 2 germanium 2 material in 1997. In this sense, it's a good agreement between the community that the magnetocaloric effect is the most developed in terms of technology and also prototype. So it occurs that in materials, we have 3 contributions to the, where's the pointer? Can you see my mouse? Oh, no.
Yeah, we can see the point. Yeah, we can see the mouse.
Yeah, okay. So we have 3 contributions to the entropy: the magnetic contribution, lattice contribution, and the electronic contribution. For magnetic materials, we usually disregard the electronic contribution, and then we look only to the magnetic and to the lattice one. So it can occur in an adiabatic form, where we apply the magnetic field to the material in a adiabatic form, and in order to maintain the entropy 0, the lattice vibrates, and then the temperature of the material increases. In an isothermal process, when the magnetic material is under a magnetic field, the alignment of the moment with the magnetic field direction will lead to the movement of the lattice, and then it removes or absorbs heat from the external environment. So usually we look to the variation of the entropy or the variation of the temperature for this type of technology. In terms of prototypes, it will occur in a cycle of magnetization and demagnetization process, where it will increase the temperature and release heat, and then when it's demagnetized, it will reduce the temperature and then absorb heat. In terms of prototypes, in 2014 and 2016, 2 companies, General Electric and Cooltech, they launched some prototypes in magnetic refrigerations. However, we're still in 2024, like 10 years after, and then we don't have magnetic refrigerators commercially available. But Brazil is in the scenario. Commissioned air conditioning was built by the Polo Group at the Federal University of Santa Catarina, where they developed an air conditioning with 2.5 kilograms of gadolinium and 10 kilograms of lanthanum iron silicon materials in 8 EMR components that rotates to refrigerate this room. So as you can see, the room that they refrigerate is almost the size of the room that contains the air conditioning. And they also use water as refrigerant, can degrades the magnetocaloric materials. So in this sense, why we don't have the magnetic refrigerators, we need to look at a number of processes that should be optimized. So we need to have high temperature variation, high entropy variation, and also diffusivity and heat, specific heat. It should be non-corrosive materials to expand the lifetime of the materials. It should have a thermal span that's large and also high cooling power. And so in the end, we need to have a low environmental impact, and they should need to be competitive in the terms of money with the currently devices. So why don't, even though the magnetocaloric technology is silent, efficient, and reusable, the intensity of the magnetic fields that we need to achieve comparable efficiencies with the gas compression systems is too high, and this increase the cost of the components. As well, to achieve high performance, we need high operating frequencies, and this reduce the lifetimes of the materials. So first we need to look at the materials. Mainly the alternatives are to find rare earth-free components, because even in the system of the Santa Catarina University, they used neodymium iron boron as the magnetic field source. And this is also another thing that we should be looking for substitute as rare earth-free materials. And there's another approach using the multi-caloric effect, that's using multiple stimulus for the caloric response of the materials. And the one that I'll be talking today, it's about using thermal management components. And in this case, we'll be talking about thermal switches. As the name says, it's a switch that turn it on and turn it off when it's connected, and can be controlled by non-thermal parameters. So when we have the system open, they have a low effective thermal conductivity, and then when it's closed, it will increase its thermal conductivity. The term that characterize this type of system is the switch ratio. That's the reason between the heat transfer, the on stage between the off stage, and is the effective, mainly the effective thermal conductivity, and then we mainly use the effective thermal conductivity at the on state and with the off state. So we use this ratio to characterize thermal switch components. They can be solid state. We have solid state thermal switches, but here we have a PZT film. When the electrical, when it's closed, the system, the thermal conductivity increases, and when it's off, it reduces. But in the case of solid state system, they have high interfacial thermal resistance. It depends on the phase transition, and at room temperature, they have low switch ratios. So for this, the work that we'll be presenting today, we will be talking about the fluidic thermal switches. Here we have a magnetohydrological system with two sources, a heat sink and a heat source. And when the magnetic field is not applied, the particles are randomly distributed. When we apply the magnetic field, the particles align along the magnetic field direction and increase effective thermal conductivity, and then the heat flow goes by one side to the other. In the case of fluidic system, they have low interface thermal resistance. They have short responses, which is good for what we want to do. That's coupled with the magnetocaloric effect. And they are easily adaptable because they are fluidic, so it's easier to manage them in different sizes. The IFMUP, the University of Porto, it's built a system for the fluidic thermal thermal switches, that the match system, magnetically actuated thermal switch. That's a vertical arm where the magnetic field goes up and down. And when is in the off stage, the fluid is in contact with the heat source, that's a peltier. And when the magnetic field approaches, it goes through the heat sink and releases heat, decreasing its temperature. So with the thermal camera, we can see that after 300 seconds of operation, the heat is transferred to the heat sink. And in a rotating operation system, we were able to turn on a LED with 10 watts of voltage. But after 10 hertz of operation, there is a decrease in the span temperature. This experiment was performed using a commercial fluid from supermagnet of iron 304. And this is because it has a high viscosity and lower saturation magnetization. So we need to look for materials with it that's lower cost, because the commercial one is a little bit expensive, with a higher effective thermal conductivity and lower viscosity. So we look for another ferrofluid to test in this system, and we choose the manganese iron 204 because the group from Requinte, the chemistry group at the University of Porto, have developed a protocol to synthesize this type of system that is chemically stable and has a higher saturation magnetization than the iron 304. And we mix it with ethylene glycol and water solution, because ethylene glycol is already a refrigerant material and has lower viscosity and also higher thermal conductivity. We performed the experiment. This is the photo of the real device. And we performed the tests using frequencies of operation from 0.01 to 1 hertz with a source at the peltier heat, and the higher magnetic field achieved with this neodymium iron boron 60 millitesla. And we changed the volume of material from 50 to 100%. I will call the filling ratio. Okay, so increase the filling ratio from 50 to 100%. To understand the effect of changing the volume of material, because the convection heat also plays a role in the transfer, in the heat transfer in the system. So this is a typical curve that we have from the device, from the system. So we record the cold side. So the cold side is in contact with the environment, and the hot side is in contact with the peltier. When the system is turning on, we have a reduction on the hot system side and an increase on the cold system, in the temperature of the cold system side. And when we compare the MFO with ethylene glycol with the commercial material, what we observe that, of course, increasing the filling ratio, we increase the switch ratio. So here we have the effective thermal conductivity ratio at the on and the off stage. So this is the switch ratio. So we have an increase in the switch ratio that almost double in comparison with the commercial fluid. And when we look to the shape of the change in temperature and compare with the commercial one, we see that there is a difference when the magnetic field is applied at the on stage, that this ring size here. We have a reduction, and then a faster reduction, and then an increase, and then another reduction. So what we thought is that we have 3 changes in the effective thermal conductivity when the magnetic field is applied. So it will depend on the distance between the magnetic source and the fluid. So we looked one cycle. So we have here divided the three different thermal conductivities. So this was simulated, and we got a real close shape of the curves. So this expands the contact between the fluid and the heat sink. And this is why using ethylene glycol and water is more effective, because it expands the time of contact between the sources. And this is why we are going to use this fluid for the couple with the magnetocaloric material. So this work is already published at the Energy Journal. And if you want to take a look at more details on the simulations and also the experimental part, the reference is here below. So the question is how to couple the magnetocaloric effect with a thermal switch. Well, there were some calculations performed by Kitanov's group. That's a really active group in the terms of solid state refrigeration. And they simulated a system where we have a magnetocaloric material sandwiched by two thermal switches, fluid thermal switches, and then we have a heat source and a heat sink. And the magnetic field is applied. It aligns the second thermal switch system, releasing heat through the heat sink. And when the field is removed, the net magnetic field is enough to align the first thermal switch to absorb heat from the source, and then the cycle begins again. So they performed the simulation using the heat pipe package. It is based on the implicit method, considering 2.3 milligrams of gadolinium and 1.4 milligrams of iron-based fluid. It has a switch response of 5 milliseconds. And they simulated with an operating frequency from 20 hertz. It's a really high operating frequency. Okay. And what they achieved from the calculations is a temperature span. That's the difference between the ambient temperature and the material temperature of 1.12 Kelvin with a coefficient of performance of 8.5. It's a high COP value. But we will try to achieve this with the magnetocaloric material and the thermal switch coupled experimentally. Daniel Silva, that's also a co-worker in this work that I'm presenting. He developed the heat pipe package, and he also performed calculations considering two thermal switches. But also we can use only one. If we look into this graph here, for the effective thermal conductivity of the second thermal switch as 0, if we have half of the temperature span for the magnetocaloric material, we can use only one thermal switch. And using only one thermal switch, that's this graphic, where he simulates different frequency of operations for one thermal switch at different temperatures. Close to room temperature, we achieve higher temperature variations for lower frequencies of operation. So this will be the range that we'll be working here at low operating frequencies. And the main requirement for this to work is that we have to have at least 50% of the magnetocaloric effect of the gadolinium, that's around 2 Kelvin. The thermal control is local, so we need to have a small device. And this is what we need to think about, because there is no experimental verification of both of the simulations. And this is what I'm here to talk about. So first, we had to think what we had. So we had a Halbach array and a pneumatic system, and then we had to understand how to put both of the systems inside of 2 centimeters of diameters. So here I am looking first how the fluid behaves inside the Halbach. So when I insert a recipient with a little bit of the fluid, it goes to the edges, radial, have a radial movement. This is expected. Some simulations that can be found in the literature, where the largest particles goes first, and then the smallest one goes after. But here we have a good size distribution of 10 nanometers. So it goes all to the walls of the recipient. And then we had to think other things, like with geometry, it will be good to connect both of the systems. Which are the best thermocouples? Because we don't want interference of the magnetic field. What types of heat sinks that we will be using, and how to control the environment. Control the environment was the hardest part. We had to go to a room that nobody were working, and be sure that nobody would enter the office, so we couldn't have the effect of another body inside the room. So first we thought about the geometry cylinder, of course, and we built an aluminum-based heatsink for the environment, and to have the fluid, the fluidic ferrofluid, we used a half-cylinder recipient. In one side, we have the copper to be in contact with the gadolinium, that's our magnetic-caloric material, and a small heatsink of copper to be connected in the interface, the heatsink, the aluminum heatsink. And we also coupled a thermocouple to monitor the heat transfer at this part. This is the full system. We have the albacarre, the pneumatic system, and we use one thermocouple for the environment, one thermocouple for the gadolinium, for this gadolinium side, one thermocouple for the interface, another thermocouple for the interface with the heatsink. And the albacarre has a field of 1 Tesla. And this work is submitted to the International Journal of Refrigeration, and it will be released soon, I hope. And we monitor all these temperatures change to characterize our proof of concept prototype. So this is how the system works. We put the gadolinium, so magnetic caloric material, in height high enough so it will not touch with the fluid when it's outside the field, and it will operate in a cycle where when it's outside the field, the heat convection is the only mean of heat transfer. And when the magnetic field is applied, the magnetic caloric material increases its temperature, and the fluid gets in contact with the magnetic caloric material, transferring heat to the heat sink, and when it's removed again, it begins the cycle. So we use 7 grams of gadolinium and 1 milligram of ferrofluid in this device, and we test both ferrofluids, the commercial one and the ethylene glycol one based. This is a typical curve that the main temperatures that we look for is a temperature variation of the gadolinium, the environmental change of temperature, that's the base temperature, and we take the mean, the movable mean of the temperature of the gadolinium to evaluate the parameters. So we are operating a very low frequency, 0.004 hertz, 0.001 hertz. I'll be talking about this in a little bit. So we look for the temperature span of the gadolinium. That's the temperature of the gadolinium at a given temperature less the gadolinium temperature when we begin the cycle. And we have here 3 measurements: the gadolinium alone, and when the gadolinium is in contact with the ferrofluids. As you can see, and the dots are from the mean movable mean temperatures. So the first thing that we note is the heat transfer rate per cycle is larger for the system coupled with the ferrofluid. However, after several cycles, there's no gain in the temperature span. But in a mistake, it was actually a mistake, we From asymmetric cycles, where we gave less time for the material to heat when it's outside the field. So we magnetize and it increases its temperature. And when we demagnetize, it reduces, then increases again before we magnetize again. So we gave less time for the material to heat up before being magnetized again in asymmetric cycles. And what we observed is that the temperature span reduces faster, and we could reach 0.6 Celsius degrees of variation when we put the system 2 minutes inside the magnetic field and 15 seconds outside the magnetic field. So asymmetric cycles promote the temperature span in this type of system. For the gadolinium alone, that is the triangles, as you can see for the, we call refrigeration zone when the difference between the temperature of the gadolinium and the environment are negative. So we call this refrigeration zone. It's larger for the coupled system, but it's even larger for the manganese iron oxide particles in ethylene glycol. When it's 15 seconds outside, but it's maximum for the commercial one with 10 seconds out. This, we think, that might be related to the viscosity of the material, of the fluid. And so asymmetric cycles promotes temperature span. There is a maximum. We didn't go through this yet. It should be further evaluated. And when we look to the coefficient of performance, the symmetric cycles, we achieved a COP value close to 8. And the simulations of Kitanovsky group was 8.5. So even with a small device and using only one thermal switch, we could reach a COP value close to the theoretical one. So this is a good thing for our prototype. The COP values at the asymmetric cycles did not increase. What we could increase was the cooling capacity. After 400 seconds of operation, we achieved higher cooling capacity for our small device operating asymmetric cycles. So of course, if we take a long time, asymmetric cycles achieve lower temperature spans, and this is why we have a higher cooling power. But the COP takes into consideration the whole cycle, and we didn't gain in the asymmetric cycles. We performed also simulations using the heat trap pipe package in the discrete method. And if you look here, we have this term. It's the ratio between the time fraction in the off state. And for higher periods, as we have here, 240 seconds, for instance, there's a limit where this value tends to reduce. So of course, there is a gain when we give less time for the material to heat up, but we have a limit when this will work or not. So in conclusions, ethylene glycol in water solution promotes heat exchange efficiency in the thermal switch. Low frequency operations, it's better for practical applications. This is the first experimental evidence of a coupled system of magnetic caloric effect and thermal switch. Symmetric cycles, that was we made a mistake and then we find something. Asymmetric cycles enhanced the T-span and also the cooling capacity. In the future, we aim to understand the viscosity effects in this type of systems, and also perform the experiments with other magnetic caloric materials. In the future, we aim to use the multi-caloric effect, that's couple the mechanocaloric effect with the electrocaloric and magnetocaloric effect. The type of materials evaluated in this type of systems are For instance, PVDF, it's a polymer. Heusler alloys like nickel manganese base, nickel manganese-indium, nickel manganese gallium, nickel manganese cobalt are also evaluated. And also here we have gadolinium silicon germanium. That's also material that I'm used to work to. In the middle here, like we have the mechanocaloric with magnetocaloric, electrocaloric, and magnetocaloric materials. But in the middle, we don't have materials to put here. And I believe that the ones that should be here are the composites. So the composites, for instance, made of PVDF and alloys will be here, or PMN also will be here with copper, zinc, aluminum, for instance. So this is the type of research that I'm performing right now, is to build composites to merge this caloric effect, then control the hysteresis using applied pressures, for instance, to enhance the caloric response, have a good reproducibility. There is few works in the literature, mainly from the Gucci-Flash group, where they already observed the reproducibility on the multicaloric cycle. And from mixing different phases, we can also have the rise of new functionalities, for instance, like the magnetoelectric coupling that can also be used as sensors. So I would like to acknowledge the group where this work was performed at the IFMUP group, and also the institutions that finance this work. And thank you for your attention. And I hope I was short in time. Sorry for being so fast. So we are open for questions, like we can discuss these results.
Okay, muito obrigado, Vivian Andrade, por your nice talk. Bien, ahora pasamos a los palestrantes, a los panelistas. Los panelistas que tenemos el día de hoy. Por ejemplo, tenemos a un invitado que nos visita regularmente. Él es un venezolano, un profesor del IBIC de Venezuela, pero ahora está en Pelotas, en la Universidad de Pelotas, el profesor Pedro Silva. Pedro Silva.
Hi, Pedro.
Nice presentation. I have no question for ahora. Thank you very much.
Thank you.
Ok, Pedro, no hay problema. También tenemos de México el profesor Arturo Martínez. Arturo, del CBPF de México.
Sí, buenos días, Luis. Muchas gracias por tu presentación.
Thank you.
No tengo preguntas por ahora. Gracias.
Well, okay, let's continue with Professor Stuart Holmes, University College London and University of Cambridge. Stuart?
Thank you, Vivian. That was a very nice talk. A lot of information. It's not exactly my field, so I
tried to be concise. I tried to be concise.
Nice. In terms of competing with, say, domestic refrigeration, say the time scale and the temperature change, can you compete with those at the moment, or is it still at a research level? What level are we in terms of replacing domestic refrigeration with magnetocalorics?
I'll be back here in the case of this prototype, that this is the most advanced prototype reported so far.
Yeah.
So it can operate in over 20% of efficiency. It's not the theoretical one, but it's close to. And we had also our workshop on caloric effects that was like 2 weeks ago, where the Guilherme, that was one of the developers of this prototype, he said that if you go inside this room, it will be cool with 26 Celsius degrees here in this room. So it's not competitive. One of the questions that I made to him was how much it would cost if you say to a company, hey, buy this air conditioning. How much? He said hundreds of thousands. So reals. So it's really expensive also because you use around 14 kilograms of magnetic material. So to be competitive with the gas phase is still, we have a lot of work to do. And when I talk about the multicaloric cycle, using multicaloric effects, that's using pressure and magnetic fields simultaneously or alternatives, it reduces around 70% the intensity of the magnetic field. So I hope, this is me talking, that with the multicaloric effect, it will be more competitive. There is also another path with the magnetic caloric effect is to use the magnetic caloric effect in some components of the conventional gas system to increase the performance. I believe this is the more approachable and more realistic thing, that's to use the magnetic caloric with the gas phase. There's another path, that's the green cooling agreement, that is to come back and use natural gases. Methanol, butanol, because nowadays we have more robust systems that will not cause any harmful for the people using. Because back in 800, a lot of people died because of the use of natural gases as refrigerants. So there is both paths. I hope I answer your question.
That's very good, thank you. I have one more comment or question. In your closing statements, you mentioned the Heusler alloys were potentially useful. What property of the Heusler alloys are you accessing for this scheme? I know they're important in electronics, for say spintronic devices, some GMR, TMR sensing, but what aspect of Heusler's are you taking for your research?
So here, you mean here?
Future, this one, yeah.
The nickel manganese indium and the nickel manganese gallium, for instance, they are being investigated because of their Martin-Cittig transition.
Yes, okay.
And for nickel manganese gallium, for instance, the Martin-Cittig transition depends on the ratio between manganese and gallium, is around the room temperature. So we have the largest entropy change, magnetic entropy change. So this is the materials that we are looking for. Most of the community are looking for the nickel manganese gallium, nickel manganese indium, and nickel manganese tin.
Okay. I mean, I think these materials, they're a bit better understood now, and they're able to be made in a purer form, say, things like that now.
Yeah, there's a lot of studies on how to obtain this phase without too much thermal treatments.
Yes.
For instance, one work from Bruno, that was a PhD student from Mario. What he observed, that for iron 2 manganese silicon, for instance, if you don't make the quench after the annealing, it will crystallize in the cubic structure. That is the one presenting the Martin-Cittig transition.
Yeah.
And if you use pressure, that's also another studies performed at the Sirius, you can also stabilize the phase. So it's still under investigation, the best approach to obtain pure phases, Heusler alloys.
Yes.
So it's an ongoing study.
It's good to hear that they've got applications here as well as electronic. That answers my question very nicely. Thank you. Thank you, Vivian. Very interesting presentation.
Thank you for the questions, Stuart.
Thank you.
Thank you very much, Stuart Holmes, for your questions. Bien, recorramos al público que nos sigue a través de las redes sociales puede dejar sus preguntas y al final, si alguien deja sus preguntas, transmitiremos esas preguntas a la palestra.
Blanca has a question.
Bien, ahora tenemos las preguntas de la profesora Blanca Rojas de la Universidad del Oriente en Venezuela. Blanca.
Hola, buenos días. Voy a necesitar que usted le traduzca.
Blanca, ¿puedes tu cámara, por favor?
Hi, Blanca.
Blanca, ¿estás? Parece que Blanca tiene problemas con su transmisión. Bien, si no, volvemos con Blanca dentro de un momento. Continuamos entonces con la profesora Margarita Sánchez del Instituto de Materiales de la de México.
Sí.
Margarita.
Yes, it's the CMAB, is the Advanced Materials Research Center. We are CONACYT Center. Thank you very much.
Hi, Margarita.
Hi.
Nice
Thank
to
you
meet
very
you.
much. Nice to meet you too. Thank you very much for your presentation. It was very interesting. And since you mentioned that rheology is very important, and I have a couple of questions or comments. In the systems that you compare, the iron, the commercial one, which was iron ferrite. I mean, just the ferrite made of iron, and the other one was a mix.
Two ferrites, two spinel structures.
Spinels, yeah. The other is manganese,
Yes.
a mixed ferrite. And
This one.
I was wondering if because viscosity or rheology will depend on.
We actually call rheologic materials when you have particles at the micro scales. When you have a nano scale, then you call ferrofluid. So there is a limit between the two, but they are both thermal switch fluidic systems.
But both of them, they have more or less the same size. I mean, one is 10 nanometer, the other 12 nanometer. The concentration is similar. The solvent, I don't know if I don't remember if it's similar or is it different? The
No.
second is oil,
No.
right?
In the commercial one is an oil, paraffin oil. It's polyalpha olefin is like a paraffin.
Yeah.
And here we have ethylene glycol and water. So this one has a higher viscosity than this one.
So do you have any idea on why is the difference on the viscosity or the rheological behavior? Because do you think that one of them is less well dispersed or more agglomerated than the other one? Because the concentration is similar, the size is similar. Of course, the solvent is different. One is ethylene glycol, the other is the oil. Do you think it's because of the oil? I mean, the solvent?
In both cases, the particles are well dispersed, and they're also very stable chemically. Because this one is a commercial one, like you can buy. People buy this one to make like schools presentations and demonstrations of iron fluid. People like to see the iron fluid, but in both cases they are well dispersed, and the difference is actually the fluid. Because here's a polymer. It has a different construction in terms of molecules because it's more concise and everything. And when we look to the experiment, we can see that when is the paraffin oil, because it's higher with higher viscosity, when the magnetic field approaches, it goes all up to the other side. And in the case of the ethylene glycol and water, it goes more slower to the top, and then it makes more time of contact. So this is because of the fluid itself.
Okay.
We have here a higher saturation magnetization, but iron 304 is also have a very strong saturation magnetization at room temperature. So here, what we believe, we didn't perform this study yet, but we believe that's mainly because of the viscosity. The viscosity is playing a role, and since we have a lower viscosity here, we have 3 changes on the effective thermal conductivity. So if you look here, with 0.6 centimeter, we have the material starting to go to the heat sink. With 1.2, it goes almost out to the heat sink. And when it's far away, there's still material in contact with the heat sink. So this expands the time of contact and also the heat exchange transfer as well. So it's mainly because of the viscosity.
Okay, and my second question is regarding the other materials that you show that have, show promise, like these alloys, and that you mentioned that, of course, they need some thermal treatment, and the thermal treatment is very important the way you do it, because you will get one phase or the other one, and one is obviously more interesting for the application. And I was wondering, because do you think it's going to be, I mean, I don't work in this area, right? So you mentioned just before that the magnetorheological fluid can be nano or micro, and I imagine that when you perform such thermal treatments, the particle size of the materials, of course, increases. It increases, and you get some sinterization or agglomeration. And I wonder if if this is a problem, or is this problem already solved, or the way people formulate the fluid after this thermal treatment. I mean, do you need to perform some milling in order to get again a good dispersion? How do they manage this? Or is it a problem that needs to be solved as well? Because
it is actually a problem.
Okay.
It is. It is because when we synthesize at the book form, usually using arc melting or induction furnaces. And in this case, we have a book, and to make them micro, we usually use ball milling, or to make nano, we use PLD, for instance, pulsed laser deposition. And they are highly oxidants. They oxidize a lot. And we need to perform studies on micro milling, micro sizes, and then perform further heat treatments. I already did this, and we don't have too much change when we put in the ball milling and make heat treatment afterwards. There is no larger changes in the size of the crystallites, but we have the oxidation issue and also contamination from the balls. In the PLD case, we have the amount of sample produced is really low. When I produce some gadolinium silicon germanium nanoparticles, I achieved like 0.5 milligrams of material after like 1 hour of deposition. So this is a problem. Obtain these structures at the micro and nanoscales with good magnetic properties, it's a tough task. And then implementing them on polymers, that's my goal, is one path to avoid the oxidation and also the changes on their structure, because the polymer will work as a shield for them. So this is my line of work today, is to implement them on polymers to avoid this kind of problems.
Okay, thank you. Thank you very much.
Thank you for your questions, Margarita.
Well, thank you very much, Margarita Sánchez, Centro de Materiales de México, ¿no? Bien. Ahora, creo que ya está en línea nuevamente la profesora Blanca Rojas de la Universidad del Oriente en Venezuela. Blanca, ¿está?
Sí, ¿me escucha?
Sí.
Ah, perfecto. Disculpen que se había caído la internet. Bueno, era que hay una transparencia 22 donde ella presentó un delta de temperatura y quería saber si esos cambios tan pequeños eran significativos. Un delta de temperatura.
22. Here.
El siguiente,
This
creo.
one?
Ese. No, este no, el siguiente. Ese. El eje Y, que tiene un delta de temperatura que me parece muy pequeño. Quería saber, porque yo trabajo con calorimetría diferencial de barrido, entonces, bueno, no, sé que es algo distinto, pero se me hace que estos cambios como muy pequeñitos.
Sí. Yes, it's small. It's small. It's 0.6 Celsius degree. However, it's half of the theoretical one. The theoretical one for the system using two thermal switches was 1.12 Kelvin. Celsius degrees, it's a difference of temperature. So a temperature span of 1.12. And here we have a temperature span of 0.6. So if we consider the losses from the environment, we have a quite good temperature span. But we also need to look at the coefficient of performance and also the cooling capacity. We had a cooling capacity of 0.7 watts. And if we normalize this by the amount of material that we have, of 7 grams, if we compare with the efficiency of the air conditioning, we achieved almost the double of their performance, the efficiency of their performance. We don't look only to the temperature span, we also need to look at the other key parameters. And here we have the coefficient of performance close to the theoretical one in the symmetric cycles. Although it seems small, we also have a small device, it's this size. For the temperature that we were around 30 Celsius degree, it's a good temperature span. It seems small, I know, but it's close to the theoretical one. And this is a proof of concept.
Gracias. La segunda pregunta era sobre las perspectivas. La primera que presentó de las perspectivas hablaba sobre el efecto de la temperatura ya. Sí, esa. El elastocalor, o sea, las perspectivas en las medidas elastocalóricas. Yo trabajo con polímeros y me interesaría qué perspectiva tiene ella allí.
I have one collaborator, that's Alexandre Magnus, that he built a system that can apply hydrostatic pressure in thermoplastics. So it's one of the ways that I will be measuring the barocaloric effect. I have a piston, and then it can control the strain changes and also the temperature variations.
Okay.
And here at CBPF, Felipe just defended his PhD. He has a gauge, a strain gauge, where you can apply in one direction. So it's the elastocaloric measurement. Okay. So this is the type of systems that I'll be using to evaluate the mechanocaloric effect.
Okay, gracias.
If you have interest, we can talk about this later. You can send me an email.
Muchísimas gracias y felicitaciones. Congratulations.
Thank you.
Ok, muchas gracias Blanca Rojas de la Universidad del Oriente en Venezuela. Bien, ahora vamos a pasar, nos vamos a Chile con el profesor Sergio Conejeros de la Universidad Católica del Norte en Antofagasta, Chile. Sergio.
Yeah, I'm here, so can you hear me? Okay, so
Yes,
thank you very much for your talk, Vivian. It was very
thank you,
interesting.
Sergio.
I'm not expert in your field, but I have general question. I suppose I can look for them in the website on Google, but you are here, so I'm going to take advantage that
Don't worry,
probably
we are here for this.
time for me. So I think in the slide 25, the magnetocaloric effect. Why gadolinium is so important for magnetocaloric effect? So, do you have other options for gadolinium based materials, or can you say something?
Yes. I didn't talk much about the materials. I could because I had time. I thought I wouldn't have time to talk more on this. But gadolinium is the reference material when we talk about magnetocaloric effect, because it has a transition of second order. So it does not have a structural change from one magnetic order to the other. As I mentioned, the milestone for the magnetocaloric effect was the discovery of the giant magnetocaloric effect in the gadolinium-5 silicon-2 germanium 2. So after this discovery is when we have more production of prototypes. But they are also based on rare earth. Gadolinium silicon-2 germanium 2 undergoes a first order phase. So when it changes its structure and come back, the material breaks. This also happens with the Heusler alloys at the martensitic transition. So it reduces the lifetime of the material. So after several cycles, you have a loss. In the case of gadolinium, since it's a second order phase transition, it does not break as the other ones. And gadolinium temperature diabatic change is around 10 Celsius degree, and gadolinium-5 silicon-2 germanium 2 is around 20. But after several cycles, you have a reduction for the gadolinium-5 silicon-2 germanium 2, and for the gadolinium, you don't have. So that's why it's the reference material.
Okay, for instance, europium or terbium, they don't behave like that, right? Because
yeah, there is studies with other rare earths, erbium and terbium as well, but there is a reduction of the temperature for the phase transition.
okay, so
We want materials with the phase transition around room temperature.
okay,
That's
so
why people use the lanthanum iron silicon. That's a way to move forward of gadolinium. It's using lanthanum because it's a rejection of the minority.
okay, so I'm thinking that it can be related with the 7 ampere electron of gadolinium, right? So
Yes.
yeah, so I'm thinking about that. So, but in the gadolinium based material are really alloys, right? So they have metallic properties. Or for instance, you can use gadolinium +3 base material, for instance, or it's not the case. So
I didn't understand that. Gadolinium, it's a
yeah,
form.
because in gadolinium in alloys is 0, so it's like you have this kind of material have metallic properties, but if in gadolinium 3+, when you have an oxidation in gadolinium 3+, and you have many material
Yes.
based on gadolinium 3+, so this kind of material can be used for magnetocaloric, or you just need to use alloys materials.
In the alloy, in the gadolinium silicon germanium case, for instance, you have the 3+ gadolinium.
Okay, perfect. Okay, so yeah,
You have
okay.
the 3+. But what happened is interesting is that you don't have the magnetism in gadolinium silicon germanium only from gadolinium, because you have the hybridization between the silicon and germanium contact that increases the magnetic moment of the material. It's because of the construction of the structure. You have like blocks of gadolinium, silicon germanium are connected with covalent bonds of silicon germanium.
Yeah, I
It
understand.
can be easily broken, and that's why they are interesting for magnetocaloric applications, because when these bonds breaks, the structure also change.
Okay, perfect.
That's why
Yeah,
we
yeah,
have a
nice.
first order.
Yeah, it's nice explanation. You know what happened to me with a rare earth element, that for me this kind of element are synonym of scarce and expensive. So I suppose researchers are trying to look for new materials, trying to avoid using rare earth elements, but having, you know, better or the same properties. But
Yeah.
are there
In this
some
case, there is
cutting-edge
lanthanum.
materials
Yes, there's a lot of
without gadolinium, for
prototypes.
example?
Yeah, there's a lot of prototypes using lanthanum iron silicon, because lanthanum is actually a eject when you mine the element from the earth. The lanthanum is usually the rejection thing. So I already tried to put lanthanum at gadolinium silicon germanium, and it breaks everything, reduces the temperature. It's not good to use lanthanum in the case of gadolinium silicon germanium, but in the case of the lanthanum iron silicon, it's really good. The temperature the to heat temperature can be controlled by the hydronization, and it's being replaced for the prototypes. In the case of the air conditioning, it was like 2.5 kilograms of gadolinium, but 10 kilograms of lanthanum iron silicon. It's a way to move forward from rare earth.
Okay,
That's
thank you.
not so rare. They are not so rare. They're all in China.
Oh, yeah. Okay, thank you, Vivian.
Thank you for the question, Sergio.
Gracias, profesor Sergio Conejeros de la Universidad Católica del Norte en Antofagasta, Chile. Bien, ahora nos movemos nuevamente regresamos a Venezuela con el profesor José Fermín del IBIC, Caracas.
Zulia, Universidad de Zulia,
Hi, Jose.
Universidad de Zulia, disculpa.
que pasé un tiempo en el IBE ya con Silver. No questions on my side. Thank you, Sergio. Viviane, muito obrigado pela sua palestra.
De
Muito
nada.
grato por ter você hoje conosco aqui na nossa rede. Então, parabéns.
Thank you. Thank you. And really,
Bien,
thank you for the invitation.
Muchas gracias, José Fermín, no hay preguntas. Bien, hemos terminado con las preguntas de los panelistas. Ahora vamos a ver si es que hay preguntas del público. Primero vamos a ver si es que hay preguntas de Colombia o del público colombiano. Con Ximena Velázquez, ¿hay preguntas de parte de la Universidad Nacional de Colombia o del público colombiano? Ximena.
No, we don't have questions here in our university. Only all people say thank you for your talk and for all these results. Thank you.
Thank you.
Bien, entonces veamos si es que hay preguntas del público en general. Si alguien tiene de alguno de los panelistas, o si no, preguntas a través de las redes sociales de la Universidad Nacional Mayor de San Marcos en Perú, con Melvin. ¿Hay preguntas del público?
Gracias por el pase, profesor. No tenemos preguntas del público, solo agradecimiento por la presentación de la doctora Vivian. Gracias.
Bien, perfecto, Miriam. Vivian. Bien, Vivian, ¿usted desea decir algunas palabras de despedida, hacer goodbye o
Yeah,
algo?
thank you for the invitation. Like I'm usually going to also I've been involved with the Latin America Magnetism Association, and I would be glad to help the LAFMAT in anything I can. With even participating in the talks, managing the invited people. I would be really glad to help the association. And if you come to Intermag, I will also be there working. So I hope to see most of you here if you are coming. And I think that's it. Thank you for the invitation, and I'm really glad to be here presenting my work.
Sí, varios peruanos y colombianos, paraguayos y varios latinoamericanos que han visitado varias veces la Centro Brasileiro de Pesquisas Físicas en Río de Janeiro. Sí, también he visitado ahí, ahí tengo muchos amigos. Es un centro muy prestigioso y estoy seguro que algunos de los otros miembros de la red no han visitado aún, en algún momento lo harán. Y tenemos a Vivian también, que trabaja con Flavio García, ¿no es así?
Yes.
En el CBPF. Bien.
He already made a presentation here, right? Flavio Garcia already made a presentation for you.
Not yet, but you can invite him, please. Could you?
Yeah, he told me that he presented. When I told him
yes.
that I would present here.
Yes. Yes, many months ago, because a lot of the speakers pass through here, there are a lot of speakers, and so even sometimes I am absent. At that time, I have not been here. But yes, you are also welcome to visit us again if you want. You have the links now in Zoom that we meet us every Saturday. We have the meetings, and you can join us, and you can also invite other speakers as well. Okay, we can provide you later on the list of the next talks. Okay.
Yes.
Okay. For example, I will take advantage to say you can stop sharing your screen, please. Yeah. While I am saying who are the next speakers, next Saturday, 13th of April, is Wilson Yañez from the University of California, Santa Barbara in California, and the moderator is Professor Stuart Holmes. On Saturday 20 is Rafael González, and the moderator will be the Colombians and University Nacional de Colombia, Ximena Velázquez. On Saturday 7 will be sensores basados en sistemas optoelectrónicos o optomecánicos integrados con Diego Pérez del Centro Atómico de Bariloche. El sábado 4 de mayo, Sergio Cava, Niobium Based Materials Preparation, Characterization and Various Applications in Catalysis, Photocatalysis, Energy and Piezoelectric Devices, la Universidad Federal de Pelotas, y nos estarán acompañando de moderadores Pedro Silva y José Fermín. El sábado 11 de mayo, Neutron Scattering Techniques Under Extreme Conditions, a Key Opportunity in Material Science and Research, Antonio Moreira dos Santos, the Oak Ridge National Laboratory.
He was supposed to deliver the talk today, so I'm replacing him.
Yes, it has changed. Yes, it has changed.
Yes.
The moderator will be Mario Reis from the Federal Fluminense University. Also in 18 of May will be Sergio Conejeros has inviting another speaker, and on 25 of Saturday, May, Gabriela Di Carlo, Instituto per los Estudios di Materiali Nanostrutturati, CNRS, Montelibreti, en Roma, Italy. La moderadora será Margarita Sánchez. Bien, esos son los siguientes speakers. Y entonces creo que ahora toca a todos los presentes abrir sus cámaras, por favor, para decir, y sus micrófonos también, para decir chao o hasta luego a Vivian. Open your microphones and your camera, please, to say goodbye to Vivian. Okay?
Thank you, Vivian.
Thank you for the invitation.
Gracias.
Bye.
Bye.
Chao. Chao, chao.
Saludos a todos.
Bye, bye, gracias.